Hi everyone. Good evening, good morning, and good afternoon. So, my name is Sindhu. I'll be the host for today. Our session looks at how hardware enforced memory safety can transform the way we protect connected vehicles. With modern cars relying on increasingly connected technologies, threats like IP spoofing and rule manipulation pose serious risks to critical systems. This presentation explores the use of CHERI, the Capability Hardware Enhanced RISC Instructions, to strengthen the automotive intrusion detection and prevention systems, delivering the fine grained memory protection and scalable resilience. We are joined by two experts from Secure Elements, Saket Mohan, the founder and CEO with over 15 years of experience in the automotive industry, cybersecurity, Sampath Kalaturagi, cybersecurity and AI lead engineer and postdoctoral researcher at Lancaster University. So let's welcome them. Saket, over to you. Yeah.
Thank you. Thanks, Sindhu, for the warm welcome. So, good afternoon, good evening, in the respective time zones that everybody is listening to this. Um, I hope my presentation is on the stage. So thank you once again, ASRG, John, and the team to put this conference together. So, without further ado, so today's presentation is all about Cherry Risk 5, or Risk V, as you know, as you call it. So just before we dive into the actual presentation, so Secure Elements, we are a UK-based cybersecurity company, and we build engineering-grade automotive tool chains in functional safety, cybersecurity, security operations center for threat monitoring. Obviously, compliance is one aspect of it, and overall, the idea is to enable the entire lifecycle management here. So the company was founded in 2022 by myself, and then over time we have increased the team size. And I'm glad to have Sampath, who is our lead AI engineer, on this call as well.
As I said, my name is Safid, and I'm the founder and CEO of Secure Elements. I have been into automotive cybersecurity from past quite a few years. I worked previously.
Okay, is the screen still visible? Thank you. Sorry, there was an echo which was continuing in the background, hence the distraction. So apologies. So Sampath, do you want to just kindly introduce yourself?
Hi, I'm Sampath. I'm currently working as a lead engineer on the Secure Elements, and I'm currently working as a postdoctoral research fellow in the Lancaster University. So mainly we are focusing on the cybersecurity, AI, and automotive cybersecurity research.
Thank you. So today's presentation will go through mainly around the objectives of using Cherry, what Cherry is in the first place, because this is quite an important topic for the automotive sector. So some background model information on the Cherry and the threat model. Why did we particularly use Cherry in the context of intrusion detection and prevention system? We'll then show you some information about how did we experiment this setup, and then obviously we'll show you some of the key learnings from the project. So as the title sounds, enhancing automotive IDPS with Cherry-based memory protection. So I'm sure most of you on the call would be familiar with this picture, dated 1972, is when NIST kind of firstly published uh, the security concerns, in a way that computer can run a software. So it's been more than more than 52, 53 years now, and we are still kind of discussing software vulnerabilities and memory vulnerabilities. So that kind of shows that surely we would have kind of imagined that we are secure by now, but hey ho, we are still not in that kind of in that area. And of course, gradually things are getting worse. as well. So the major known, software vulnerabilities, especially, Project Zero, and I could name, more than a few. I've just put three most kind of common, the common known ones, which is the Project
Sakit,
Zero. Yes, hi John.
apologies, I don't mean to interrupt, but can you put the presentation back in full screen mode?
Is that better?
There we go. That looks much better. Thank you, sir.
It's just that I keep on hearing a lot of echo as soon as I put my presentation on full screen mode. That's the reason I minimized it. Okay, I think let's continue, John, on from here. Let's see how this progresses. Yeah, so some of the major known kind of software vulnerabilities, Project Zero, Chromium was one of them, and of course the Microsoft kind of Blue Hat 2019. So all of these kind of areas point towards that there are serious software security concerns, and not all of them originate mainly from software. They are mainly around secure system design, but also around hardware security. And the reason to say so is that it's a kind of a pyramid that goes right from the memory access, kind of architecture, right from the hardware level down, then up the ladder to the CPU, and then the software, the services, and the applications. So you'll find three keywords here. So obviously, cybersecurity, generally best practices, monitoring, patching of those vulnerabilities, is why this slide is particularly called "Fix the Foundations." Try to create less vulnerabilities in the first place, which in turn could mean various things to various people on this call. Could be meaning good software development practices, secure software by design, software development lifecycle, and then the list goes on. But equally, it also means that protect against more severe vulnerabilities right at the root, which is obviously at the hardware. So just a brief about what is, and why do we need Cherry. So obviously security is a top paramount kind of priority in all of the critical sectors, which includes automotive, medical, any server based platform. And we have seen the gradual rise of this exploitation, obviously cyber crimes increasing over time, and the numbers kind of speak to itself. So therefore, the problem statement is that not all security issues can be, countered by just following a secure, design approach, or on a or a pure, software, guidelines based approach. So a more effective approach is kind of needed to ensure a robust, secure system. And this is where we kind of introduce the Morello Cherry architecture. So again, for people on this call who are not very familiar, so in 2014, ARM has started collaborating. They collaborated earlier with Google and University of Cambridge and the SRI International to come up with this Cherry. So Cherry stands for Capability Hardware Enhanced RISC Instruction. And Morello is a prototype architecture that basically takes in this Cherry and puts it onto an ARM architecture. The one of the boards, or one of the early FPGAs in this area, has now been in operations, I think since 2016, 2017. um, and this uses ARM v8, Arch64 state. So kind of Cherry has two main kind of basic principles. One is introduces something called as capabilities, and capabilities and bounds. So basically, such as addresses, address ranges, and capabilities are then held in registers or memory locations. And basically, those are used for mainly two operations: code pointers and data pointers, respectively. And what this does is that this particular capability within which resides, in those registers and memory, actually enables Cherry to provide you that kind of finer grain memory safety. So which means at a memory level, but also introduces a concept called compartmentalization, which means, as you can see in the figure, that if an attacker even manages to get access to one of the compartments in one zone, it doesn't mean that the entire kind of box is contaminated. They would need further access to that particular segment or compartment, and hence keep a notice of the keywords compartmentalization, finer grain memory capabilities, Cherry bounds. So these are 4 to 5 keywords that will keep coming up in the course of our presentation that both Sampath and I are doing. And then the next slide is kind of showing exactly what I just mentioned. So on the right hand side, you have this big, kind of CPU FPGA, which we have access to currently in the UK. And this is where most of our kind of research is currently ongoing. And then on the left hand side is exactly what I said. So getting access to a thread does not mean that you are contaminating all the threads, but because you are exactly pinpointing the capabilities or the pointers, you basically are, in that specific region only. Again, something for the community to notice, obviously, because it's a new tool chain, it's a new architecture, therefore the entirety of the stack is very, very new. Obviously it comes with a revamped CPU and instruction set architecture, which is cherry oriented. uh, Obviously comes with compilers and its own sets of compilers and tool chains, so the Cherry LLVM and mainly the GDBs, the system software, and of course the applications. So currently, one of the biggest kind of let's say limitation in this area is the easy access of third-party tool chains right from the compilation state. So we not in order to use any automotive protocols, which I'll just show you in a minute. Some IP, for example, which is heavily being used to develop the software-defined vehicles, and obviously most of the Ethernet, central gateway controllers and all the Ethernet nodes. Access to some IP or compiling some IP, has been a very kind of different and a difficult task on this project so far. So, let's having given you that background or context of Cherry and what Cherry does and what Cherry is used for. Intent was to apply this Cherry principles on an existing IDS architecture. So this kind of slide shows, that this is an existing architecture where you have some of the IDS sensors, as we call them, which then reports its security events to the to different kind of operating systems, AutoSAR, POSIX, using IDSRs and IDSMs, and then it transmits everything to our security operations center, which is towards the right. We basically focus our attack scenarios mainly on these three boxes. So assuming that there is a some IP based communication, is some IP based architecture, and two ECUs are communicating, Ethernet communications and some IP communications, and there is a relay attack or a replay attack, which basically means that the IDS policy file, which actually sits within a particular, memory location, could be poisoned or could be attacked. So because some IP layer sits within application, it's an application 7-layer protocol, whereby this could be used for various. And again, I'm not going into details about what some IP is. That's yet another exploratory subject. But just to focus on why this is so important in the context of IDS and the likes of Ethernet IDS particularly, is because of the tampered payloads and unauthorized access to critical ECU functions, obviously leading to catastrophic effects across the vehicle. One of the key factors for our project was to protect the policy integrity. So often we tend to forget, while putting in place the IDS policies, the policy integrity itself, which could mean that out of the many attack impacts, one of the key impacts is the altered policies, which could allow the attackers to then manipulate or legitimize a particular set of traffic which was not previously kind of whitelisted. So therefore, how do we protect the policy file of the IDS using Cherry principles is what the idea is. And this is kind of that attack scenario. So IDS policy is stored in a non-secure memory area, and this is happening today. We have seen evidence of it. Sometimes IDS policies are kept unsigned. Distributed placement, because IDS is placed on distributed architectures, could be CAN on one and could be Ethernet on the others, host on the others, a mixture of CPU based IDS or a host based IDS, Ethernet switch based IDS. So there are significant kind of variance across the topology, and therefore accurate placement of these policies are equally kind of it has to be deterministic, kind of in that sense. And again, unsecure memories which can be exploited to change the policy file. So application of this, our objective on this small piece of let's say project was to apply the capability based security best practices of Cherry on this IDS memory rule set. Scope was very much kind of limited in terms of memory safety, prevention of unauthorized access. And the proposed solution is we basically use Cherry set bounds principles to isolate this IDS memory per region, or you can call it per ECU in this case. And the expected outcome is that this rule manipulation could then be limited, or could be kind of further blocked in order to reduce the potential damage and the impacts thereafter. We have used Cherry BSD in the Morello hardware, as you can see rightly on the top, to test this IDS functionality. So next, I hand over to Sampath, who is going to describe the model and basically take you through the next steps. So Sampath, over to you.
Hi, this is our Cherry architecture. So we define the different memory location for each ECU rules. So in that case, we define the a number of ECUs for the memory regions for each ECU. So then we use the packet sniffer, and then we use the rule validation. Based on that, if any attacker do the attack, so packet will validate with the rule, and if it is a noted that there are certain area that rule flag as an anomaly, so that we use that Cherry capabilities, that memory bounds and capability based access control and pointer integrity and pure cap and fine grained permission. So this was the architecture of this IDS. So yeah, in the normal C architecture, that's pointers are pointers going one by one, like increment procedure for the each memory location. But in Cherry architecture, we will allocate meta tag for the each memory location. In that case, that memory buffer overflow is not happening with this Cherry. So that's how that this security designed by security feature added by design. So that's okay. Can you go to next? So we achieve the key result that IDS one functionality, like even though that network we monitor the network traffic and we detect the attack, even though some if someone is spoofed the IDS rules and get the access to the IDS, but it can't change the IDS rules because of that memory safety. So there's a we were able to deploy this whole system on the Morello board and simulation, both as a ECU and the IDS. Yes, okay. In the demonstration, we capture and analysis the packet. So how IDS captures and analyzes ECU traffic, and IDS rule design for respect to each ECU and separate IDS memory location, as I tell in the previous slide. So that's what we have done with Cherry here. So this is some of the screenshot from our simulation. So in the left hand side, you can see some IP packet features. Based on these packet features, we define the rules for the IDS. And in the right hand side, you can see that that is simulation. That's kind of simulation. Yeah. It's in the background, we have done the packet snipping, that how is this packet going, and the IDS running, that if any rule violated packet identified from the IDS, we can check with our packet snipping script. So that's how that simulation work. So here in the left hand side, you can see the rule matching, that if some packet get the exact IDS IP address and get into the IDS, got the IDS access. But if you're trying to manipulate IDS memory, it will restricted by that memory safety feature of the cherry. In the right hand side, you can see that when attacker trying to manipulate this memory, that code dump message coming out from the system. Can you move to the next slide? Okay. Yeah. Yeah, this is how that memory safety and then CHERI and Morello help to meet the objective that we make the memory safety with the capability model. This will help to enhance the security and resilience because even though that someone compromise the system, they can't compromise the IDS. They can't manipulate the IDS rules because the vehicle is a vehicle, and most of the critical infrastructure area they have some critical functions. Like if you think about the vehicle, there are some normal issues, then high critical issues. But if you uh, categorize these IDS rules based on the ECU priority. In that case, if someone compromise the IDS, they can't manipulate these ECU rules and they can't access other compartments. So in that case, we can ensure the safety of the system. Can you move to the next? Yeah, this is the simulation video which we took from our simulation. I think it's not much clear here.
So on the top left, you can see the Ethernet IDS, both the some IP packet generator, the receiver, the attacker model, and then on the extreme right hand side below you, basically this is where we are trying to manipulate. But then because of the cherry bound capabilities, it's not letting us, let's say, exploit the region. So in a nutshell, kind of demonstrating that basic principles of cherry, can be used to enhance the security and the integrity of the policy files of the IDS. So, obviously, with all that done, there are some challenges and the blockers that I would like to kind of bring to the fore. Firstly, for particularly for us, for me, Sampath, and the team in general, this has been a excellent learning kind of curve, because so far the automotive industry has not been, we have not been used to using such kind of techniques and technologies. So adjusting our knowledge, particularly around the architecture itself, has been a great learning curve. We have learned made things around capabilities, pointers, and cherry set bounds. As I previously mentioned in my opening brief, there are some limitations across the tool chains around third-party library compilation, which are still still present, but with new companies and government-funded projects opening up Cherry to different critical sectors, particularly in the national infrastructure, power generation, etc. This tool again has shown, we have shown great interest, especially to the UK government, in by using projects in the UK that could be used for automotive grade projects. And then there has been some challenges and kind of learning for the team in terms of the debugging tools, debuggers, etc. Um, Obviously, we are still in that POC stage, but we have proven a point that IDS works, and IDS will definitely work on a new architecture, and it basically solves a great problem of policy file integrity, which still remains one of the core kind of core challenges across the automotive domain. So, kind of summarizing this in like three bullet points. So, further testing definitely needed, because we have done a very small POC on one board. We would like to expand this capability not just on one board, but have few more ECUs connected to the network and see how this behaves. So we definitely have our company plans to kind of exploit this opportunity and extend the capability of taking this much more further. And obviously, this becomes a long term kind of goals to help then automotive industry uptake this new architecture. Because again, not everything is kind of simple here. It's a whole supply chain, it's whole new architecture, so there are much more than what we just see on the slides here. But yes, we have made a point and we are talking to respective stakeholders in this, at least in the UK, with OEMs and tier ones, with the local government bodies here, to make sure that our voices are heard, and the technologies are kind of adopted, if not today, but maybe sometime in the future, because this is an area to kind of go. I think in general that kind of summarizes our presentation for today. And that's our portfolio of our cybersecurity offerings that we do as a company, which I will obviously and kind of advise people to look at, right from the Tara analysis to S-bombs and electric vehicle simulation. So these are some of our core offerings. But in general, I think I will stop my presentation here, and we'll be opening up for questions. Um, thank you very much for listening to this presentation.
Yeah, thank you very much.
So over to you, Sindhu.
Yeah, so you're able to hear me now? Yeah, you're able to hear me, Sakit, now? Yeah, thank you very much for the presentation, Sakit and Sampath. So we'll be now opening up the slot for the session. So yeah. So the first question for today is there a possibility to update rules? I mean, is CHERI supporting it?
If the question can be further elaborated, Michael, I presume you mean IDS rules here. If that is the case,
Yes, sir.
then yes,
You can update.
yes, yes, we can update it, Michael.
Thank you, Sakit. And then the next question is what architectural or performance trade offs must be considered when integrating CHERI enabled memory protection into resource constrained automotive ECUs running real time intrusion detection workloads?
Yeah, we are still at a stage of FPGAs, and just
Mhm.
recently we have been able to, I mean, at least in the UK, there ARM is very closely working with University of Cambridge to minimize the architecture and bring it to a prototype stage. So there is something called as Cherry IoT, um, which basically has the uh, let's say called the Cherry principles on that. So we experimented our solution on a big FPGA, like a big CPU size box. But currently we do have, uh, or let's say, Raspberry Pi sized boxes that contain these architectures. So with respect to architectural performance trade-offs, certainly this is not automotive grade yet. So therefore, there are certain limitations. We have not yet tried and tested how the cryptographic functions actually work in terms of protecting the IDS policy file or the logs that will be generated. So there are certainly major trade-offs here. But if you look at what does Cherry actually bring in, we're trying to bring in more of a hardware protection than just be limited to cryptographic protection, or maybe just the software protection that normally we use across the automotive industry today. In absence of any HSMs or trusted execution environments, companies are using software based, OpenSSL based, principles to just secure the applications. So this goes right into the heart of hardware to kind of secure it right from let's say from its origin. So yes, I mean, much work to be done here, Sindhu, but yes.
And also circuits some libraries is still not support for the pure cap architecture. So in that case, we have to use the hybrid ABI. The
Correct.
hybrid ABI is still consists with the unsanitized pointers. That was the main concern.
Correct.
Sure, sure. Thank you for the details. I
I
think
also
we have a
shared
for.
the publication that we made based on this experiment.
Okay, yeah. Thank you, Sampath. I think we have now a follow-up question on this. Yeah, what are the next steps? When will something be released? There's a question from John.
Yes, you have put me on the spot, so thank you for that question. uh, so we are closely working, John, in the UK with Department of Science and Innovation, so DCIT, Science Innovation Technology. So we are uh, um, advocating for this to be, let's say, trialed within an automotive OEM in the UK, and you can already imagine which OEM will be that. Um, and we are trying to get in that space to trial this exact technology with one of with one of our prototype, let's say Raspberry Pi type Cherry IoT boards, um, for an initial kind of demonstrator or initial kind of POC. So that is what I can kind of reveal.
Mhm. Yeah, thank you, Sakit. Um, so in the cherry perspective, there is another question which, yeah, it was connecting. So how can cherry capability hardware, enhanced risk instruction based memory protection, strengthen the resilience of automotive intrusion detection system against runtime memory exploits such as buffer overflows during runtime or the code reuse attack? So can you also throw some light on this, whether such scenarios
Yeah,
will be considered? Yeah, maybe
yeah.
Sampath. Yeah.
As I mentioned in the presentation, that normally because that automotive standard is normally seen at the moment. So normally C is going by the pointer, going by incremental one by one. So in that case, it will access unwanted memory location when we are going to their respective memory location. But when we use the cherry capability, we can assign some tag for the exact memory location kind of metadata. In that case, pointer will not go in one by one to each of memory location. It will directly go to the respective memory location. In that case, it will avoid to access unwanted memory locations.
Okay.
Yeah, because
Yeah,
basically
so
it
this
will not
should be
allow
considered
to
in the starting also in the design perspective, or it has to be redirected, or it is already taken care as a part of a design then.
part of design. Yeah.
Okay, thank you. And yeah, I don't see any more questions. Yeah, thank you, Saket, and then thank you, Sampath, for joining us and taking us through the session and also some interesting insights about the cherry. Yeah,
Okay. No, thank you once again,
Thank you.
Sindhu, and thank you, team, the SOS ASRG team, for having us on the stage. Thank you.
thank you, everyone.